So the problem that I did was 4P79, um, and that pertains to objective 4.3, which is springs and simple harmonic motion. And basically, in the question, there were two spring, um, like oscillating systems, and so they give different characteristics of the two springs. And the first one, they give the amplitude, the period, which is 2.1 seconds, and they give, it's on Earth, so the gravitational constant is 9.8 newtons per kilogram. And I just said that the mass was capital M and spring constant is Ks. And the second spring, they have a different amplitude, and it's on planet, and a different planet that has a gravitational constant of 6.8 newtons per kilograms, and the mass is 6 times the mass on the first spring, so I said it's 6m, and the spring constant is 10 times as stiff as that of the first spring, so it's 10 ks. So the general principles that I used is, first of all, that period equals 2 pi over omega. And then the second principle I used is omega equals the root of ks over m. So the first period, or the period of the first spring, I said it was T1, which is equals to 2 pi over the omega of the first spring, which is 2 pi over root of ks over m, which equals 2.1 seconds. So if I were to express the period of the second spring using the same constants like ks and m, then I thought I would be able to derive the period of the second spring. So for the period of the second spring equals 2 pi over the omega, the angular frequency of the second spring, which is 2 pi over root of 10 ks over 6m, which equals 2 pi over root 5 over 3 times root of ks over m. So basically, the period of the second spring is just period of the first spring divided by root of 5 over 3 according to the equation. That's why I divided 2.1 seconds by root of 5 over 3, and I got 1.626 seconds, which I rounded to 1.6 seconds.